Hello, is my voice audible?
Yeah, you're audible.
Um, okay, so it's 1:10 now. It seems like more people want to join in. So I suppose we can start. In this meeting, Q&A has been enabled, so I think you can use that to ask questions as well. And I think that's it. Siddhi, you can take it away.
Am I audible?
Yeah,
Okay. Able to see my screen?
yes.
All right. Hello, everyone, and a very warm welcome to all of you. Kritika welcomes you to yet another exciting Learner Space module. I'm Siddhi, and joining with me today to lead this session, we have Arha. So, before we say a single word about physics, and I want you all to look into the screen and realize something. If this entire screen represented the history and size of everything that ever existed, everything we have ever known, every person we have ever met, and every empire in human history is strapped on a rock so small it does not even qualify as a single pixel. Today, we are not looking at the small pieces, but we're looking at the entire puzzle. Welcome to Cosmology. This isn't just astronomy, but an ultimate detective story. So, over this module, we'll be touching upon where did this all come from, how is it all going to end, and how did it get there. So, first up, we'll be talking about the cosmological principle. Uh, this is basically the universal rule of average, and it states two major things. One is homogeneity. Our universe is boringly uniform, and wherever we go in the universe, it's roughly the same. The second part is isotropy. It looks the same in all directions, whether you look right, left, down, or right. The view and density of most of the things is the same. So scientists generally call homogeneity as invariant under translation, and they call isotropy as invariant under rotation. Basically, turning around does not change anything. So then you might think that the star is a giant lump of hot gas, but the entire space is empty. Why? How is that uniform? So cosmological principle does only works when you zoom out in a massive cosmic scale. And also, why do we even care about this rule? Because there are a lot of difficult math, like the Einstein's general relativity theorem, which needs tensor calculus, and it is much better this principle basically turns the universe into a predictable, smooth pool which we can easily study. So next we'll be touching up on redshift. So we all know that light travels in waves, and just like sound, the color of light will change depending on whether the waves are compressed or stretched out. We know that blue light has short, tightly packed wavelengths, and red light has long, stretched out wavelengths. So whenever a star is perfectly still, it will emit normal light. But when the galaxy moves away from us, then light waves trailing behind will get stretched out. And by the time they reach our telescopes on Earth, their wavelengths would have been much longer than and making the object look shifting towards the red end of the spectrum, basically. And astronomers basically know that light is stretched by using a tool known as spectroscope, which splits light into a rainbow like prism. And the redshift parameter is given as Z, and it's a dimensionless quantity. Uh, the formula is given in the screen. Now, you might be thinking why cosmologists cared so much about this. So, in 1920s, an astronomer named Edwin Hubble, he looked out at the universe and he noticed something very, very shocking. He saw that every distant galaxy had a redshift. And not only that, further the galaxy was, the faster it was redshifting away from us. So this hit a groundbreaking realization. If we had rewind on the universe, then everything currently which is stretching apart, it means that billions of years ago, everything would have been packed together into a dense point, and that is basically the foundational proof of Big Bang theory. So this is a small animation on how redshift works. Say you're moving away from the object is moving away from you. The wavelength is getting stretched out into the redder spectrum. It could also be because the universe is expanding. So this leads us to the two types of redshift. One is the Doppler redshift, and the other is the cosmological redshift. As the name suggests, Doppler redshift is caused when the celestial body is basically physically moving away from the space, and cosmological redshift is basically the when the very fabric of the space between us is stretching out. Let's move on. So, when physicists construct mathematical model of the universe, they map it across two domains, space and time, to ensure that cosmological principle remains true, the universe can geometrically behave in only three ways. Either it stays static, or the entire universe contracts, or the entire universe expands. So, this basically leads us to the rule of scaling. It's basically just zooming in or into a photograph. It's just the same as that. Only the magnification changes and nothing else about the image changes. So this way, a universe can be scaled, and the properties of homogeneity and isotropy, basically the cosmological principle, it remains intact. So scaling is the geometrical mechanism which allows us to model a dynamic changing universe, keeping our cosmological laws perfectly valid. Um, so if I asked you how fast a balloon was growing, you would probably just measure radius over time. But now we don't know the exact radius of the universe right now, or where it's even going to end. So that is why we use scale factor. So basically, scale factor is we can it is represented as a of t, and if t is more than one, space is stretching. If it's less than one, then it's shrinking. And if it's equal to one, then space is basically constant. So this brings us to the foundational equation of cosmology, which is basically R proper is A of t into R co-moving. Now, co-moving distance is basically, for example, you have a grid of squares and you have to count between two dots. The distance between those two dots is four uh, is four squares apart. If you stretch the feet, it will still be four squares apart. So that's basically how co-moving distance is represented. And proper distance is basically measuring the actual distance. And that is how the co-moving distance is multiplied with the scale factor to give the proper distance. So how do we measure universe with no end? Now, if you are standing at the equator of the Earth and you want to go to a city exactly halfway around the globe, you would draw, if you draw a straight line, you get one distance. If you walk along the curved surface, you get another distance. So, how do you write a single rule? Basically, you use a metric. Now, metric is a master equation which is generalized leveled up version of the Pythagorean theorem. Now, we define the a very microscopic step ds on the flat path, and then we would integrate it to get the actual real distances across the curved space. So if you are standing in a flat table, it's just basic geometry. Ds square is dx square plus dy square. Now, if you are on a 3D sphere, standing straight line grids will be useless. We use angles such as theta and phi, as you can see here. And if say this is a point x, y, z on the 3D plane, then we can substitute x as r sine theta cos phi. You can see how they got this as well. And y is r sine theta sine phi, and z would be r cos phi. And once we substitute these in the equations, ds square equals dx square plus dy square plus dz square, we would get this as a 3D sphere metric. And here is the ultimate question to tie everything together. We know that the universe is contains space, but we cannot measure the distance in space without considering time. So, to truly map out the universe, we, along with the 3D sphere metric, we have added time as the fourth dimension, which has been multiplied with a constant c, and that's basically the speed of light, with so that the units will match up properly. And so that's the 4D space-time metric, and it's written in this way. Now, let's look at the bigger picture. Basically, on the different geometric shapes that the universe can take. Um, so universe could be flat with zero curvature, or it could be positively curved closed universe, or it could be negatively curved an open universe. So in case of a normal flat universe, we have a normal equation. We will be discussing on what chi is a bit later. And to capture now after that, for a positively curved universe, we use sine pi by r to capture the wrapping effect basically because of the curved universe. And we have, in case of a negatively curved universe, we have this as the equation wherein we use a hyperbolic function. Now, see what chi basically means. Chi is basically the co-moving radial coordinate. Now, it labels a point in space on fixed coordinate grid, factoring out the expansion of universe with a of t. And because the universe is also expanding with time, so the scale factor handles the stretching part, and chi handles the structural geometry part. So if our universe was flat, then chi behaves like a normal straight line. And say it was positively curved, it behaves like a trigonometric sine function. And if it was negatively curved, it would behave like a hyperbolic function. Now let's see what the FRLW matrix means. Um, so the Friedman, Lemaitre, Robertson, Walker matrix basically. So the FRLW tensor matrix, if we break this matrix down by row and column, then it basically shows us how the universe operates. So this part of the matrix, these are the three coordinates, and since the universe is isotropic in nature, these three coordinates will expand with the same 80, with stretch with the same 80, and and the fourth dimension over here is that of time. So that's how the FRLW matrix is written. So we established that space expands, but now we need to calculate exactly how fast it is happening. So to find the velocity of a distant galaxy, um, we will basically we can take the derivative of the physical distance over time, and we get these two terms. So one of the term is basically because of how fast the universe is stretching, and the other is because of the actual moving. So we basically do not consider the local gravitational movements through the coordinates at cosmic scales. So we are neglecting this term, and we write V as R I dA by dt, and dA by dt is basically A dash. And we are taking some constant h, which is basically the Hubble parameter, and that's written by a dash by a, and that gives us the Hubble's law, which is the velocity of a particular galaxy is h into r proper. Now, let's talk more about the Hubble parameter. Uh, you can see the linear graph on the screen. This is exactly what I had mentioned before, how Hubble had plotted in the 20th century. And as we move away, as further away a galaxy is from the Earth, the faster it runs away. Uh, Basically, the Hubble parameter h will also change with time, but it takes around billions of years because as the expansion of A of t changes, h will also change. And right now, currently, h is at approx 70 kilometers per second per megaparsec. So, if the universe is constantly expanding and diluting everything inside it, what does it tell us about? So, let's talk about the eras of the universe. And uh, initially, so the first era of the universe was basically radiation dominated, where high energy light photons and particles were flying at a speed of light. Um, this hot plasma carried great internal pressure, and it fought very hard against the gravity. So the scale factor was growing very, very slowly, and that is why A was inversely proportional to under root T. And as the space stretched out, the light cooled down, and next came the matter dominated area. Matter includes all the baryonic atoms like hydrogen, helium, and dark matter as well. Since matter has zero cosmic pressure, it diluted slower than light, and gravity was finally winning, and we were pulling atoms together to build stars and galaxies. And the scale factor picked up some speed with A was proportional to T to the power 2 by 3. As the space basically kept growing, galaxies thinned out into a near vacuum, and that is when the dark energy dominated area came. Now, this is basically a very mysterious constant energy which is present in the vacuum of empty space. So, uh, basically, like matter or light will never dilute, stays fixed. It does not depend on anything. And as and when more vacuum is created, as the space expands, more dark energy would appear, and the scale factor basically just shooted up at a proportional to e to the power hp, where h is the Hubble parameter. Now let's see at what this graph basically means. So before we see the curves of cosmic history, basically this graph is plotted with the relative size of the universe and time. And you can see that there are different curves plotted for different curvatures of the universe. So before that, let's talk about what rho c is. Rho c is basically the critical density. We know that there are two opposing forces which exist. One is the inertia of expansion, where the outward momentum pushing the galaxies apart is present, and another is the pull of gravity, where there's a collective mass of all stars and dark matter trying to pull everything back together. So basically, critical density is the exact spot density where the two forces will perfectly balance each other out. Let's talk about the different curves that have been mentioned here. This curve is that of an overdense universe where the energy density rho is more than rho c. And this is the case of an overdense universe. And when the universe is shaped like a sphere, basically, the fate gravity will win as the expansion slows down, and it would reverse and slowly collapse the universe into a singularity, and that would be known as the Big Crunch. The other case is that of a underdense universe, which is the case of a negative curvature. Uh, Basically, that's when expansion will win. The there would be not enough mass to slow things down, so universe will just keep going and into a dark vacuum, and that might end up being a big freeze. And the other case is that of a balanced universe, a flat universe. Um, and this is basically perfect equilibrium, and the universe would never collapse. Now, as we had written some of the scale factors uh, in the back in about the eras of the universe. Let's actually derive them. So we will be considering a small amount of volume of the universe, dou x, dou y, dou z, and that mass density as mu. Uh, the volume would be a cube dou x, dou y, dou z that way. And here a cube A is basically the scale factor. And the density can be written as rho is mu by a cube. So we'll be assuming Newton's theorem and the gravitational law. So um, Newton's theorem basically will be considering that we are at the center of the universe in this case, and gravitational force will be considered as F is equal to minus dmm by d square. Um, and F is ma that we already know. We can use the derivative two times for r proper is r co moving into at to get this equation to finally get, and we can solve these three equations to get this relation. We are considering the critical condition, and that is when we will have the escape velocity, basically the sweet spot, as we had talked about before. So escape velocity will be 2gm by r, as we already know, and putting that into the Hubble's law, we will get this equation. Um, so we already know that rho is inversely proportional to a cube, and Hubble's constant will be inversely proportional to uh, a to the power 3 by 2. And Hubble's constant would not change sign. Uh, and we can solve the differential equation. A of t is equal to c t to the power 2 by 3. Um So we are not if we consider the critical state universe when energy is zero, then we will get this equation. But if we are considering some energy which is in zero, uh, its constant E would be written, and the Friedman equation would become this. So if we are considering uh, this row will be written as V by A square over A cube here. We can see that if in case the stretching factor is negligible, then this term will be almost zero. That's what we had derived before. And if in case it's A is large enough, then this universe would basically be a matter dominated universe. Let's derive another equation when we are considering the radiation dominated universe, the first era of universe, basically. Um, in that, basically, the we'll be deriving equations when the radiation it was a radiation dominated universe, and it was filled with radiations, which is photons. Now E is equal to hc by lambda for a particular photon, and we know that if we are considering relativity in mind, then E is equal to mc square, and the mass density would also change with time as the energy changes, and that is when we will get the rate of galaxies. We will be considering V equals AQ, and energy would be considered as hc by A, where lambda is A, and that is how we will get density would be proportional to 1 by A. And if we solve the equation again, we will be getting this term. And in case of a radiation dominated universe, we get A of t is equal to some constant into t to the power 1 by 2. So we are left with another term, the dark energy part. Um, so let's basically, we know that when we have some matter and energy present, uh, it'll be it'll exert some different amount of internal pressure relative to the energy density. So we can consider some equation of state and consider some omega, where in some part of the universe in different eras, T will be omega rho and omega can change. We had already derived where omega will be zero in case of a dominated universe, since the galaxy and dust particles will move slowly. In case of a radiation dominated universe, also we had derived what omega was, and there would be basically some high pressure because of high speed photons. And now we need to derive this, where in case of a dark energy, omega is -1. So let's derive that. So we'll be considering the density volume relation, and in some volume V, the internal energy E can be written as D equals minus dV, and total energy is rho V. And if we differentiate that, we get rho dV plus V d rho. We can use these two equations and equate and get this equation. And once we use equation of state, where equation of state from the last, which was it was P is equal to omega rho. We get this equation, and once we integrate, we get rho is equal to 1 by V to the power omega plus 1. We know that in case of dark energy, we in case of dark energy, rho will not be proportional to anything. So that is why omega has to be -1. So we get that. And then we can basically Einstein had given us a cosmological constant, which was 8g rho, 8g pi rho, and we can find the scale factor using that as well. So that is how they've written the scale factor here. So this is it from my side. I'll be answering the doubts now.
There are some doubts in the Q&A section. You can check there.
Oh yeah, one second. Um, so for one question we have is, how do we distinguish if the light is being redshifted due to cosmological expansion or redshift? Um, okay, even I'm not sure about this.
I've answered that question in the comment. I mean, if Yash has more doubt or needs more clarification, can raise his hand or let us know. Yes, Rudra.
There was a slide on densities which you people presented, right? Related, the fractions were with respect to the critical density. So, how do you basically figure out which of the given graphs does our universe follow? Was I audible?
Yeah. Um, I've actually not read about this, so I'm not sure.
Oh, sure, no problem.
Yes, Yuvraj.
So, can we go back to the slides where you were defining the mass and things like the mass density? Because in there you define two types of densities. One was the mass density mean. The other one was the rho. What is rho and why do we have to define two types of densities?
One row is basically the energy density, other is the mass density. So in previously, row was in the graph slide, row was the energy density. When we were uh, deriving the era, the different scale factors, row was the mass density.
And you divided the mass density by A cube, right? The scale factor.
Yeah, that's because the volume of the region is changing with time. A cube.
Yes,
That's
I
why we're
got,
considering
yeah,
a cube. Yeah.
no, I got that. But how does dividing by A cube change the mass density to the energy density?
Uh, no, here rho is the mass density only.
But we already have a mu for mass density, right? Unless mu was just the mass.
Uh, Rho is basically the density with just changing with time. Mu is the mass of that particular space.
Okay.
Critical density, it's fine, right? Yeah, Arham is already. Next, we have what are the experimental evidence for an early radiation dominated universe? Um, I've not read much about the experimental evidences, but initially that's how it existed.
If I may add to that answer, one of the biggest evidences we have for early radiation dominated universe, I think it's cosmic microwave background, right? Because it's like the afterglow of the Big Bang that happened earlier.
Hello, am I audible?
Yes.
Yeah, sorry, I wasn't able to unmute before. Uh, yeah, cosmic microwave background is one of the biggest evidences for whatever happened before the decoupling and recombination period. So yeah, that is one of the major.
Because I think after that we also have the Big Bang nucleosynthesis, though I'm not really sure if that's really relevant here.
Yeah, and coming back to your question, Rudra, I was trying to unmute then, but I wasn't able to. The Friedman equations have many different constants which we use to graph the plots and we can decide. So the constants we can find them depending on experimental observations, and from what we observe now, we can figure out which graph is ours, or we can at least roughly decide that what is ours, and we can see the space-time curvature from those experimental evidences. Yeah.
Can you also please explain a little more about what critical density is exactly? I didn't get that part.
I think Siddhi will be able to explain that better.
Yeah, basically, critical density is the spot wherein it's basically the equilibrium between the expansion of the universe and the gravitational pull. So it's basically the density wherein uh, the basically the equilibrium when the universe is neither where uh, it's the equilibrium between the universe expanding and the gravitational pull.
So between the accelerating force and the gravitational force.
Yeah.
Okay. Thank you.
Yeah, Faswat.
Yeah, so I was asking that someone asked that how we calculate mu and rho because both are mass density. So can I explain that I found a relation which can explain it.
Okay. So in a particular volume, mass density is written as mu, but now the universe is expanding. So that is why we define the density as mu by AQ.
I think Shashwat was asking if he also has an explanation, so I think we can listen to what he has found, I think.
Oh, okay. I'm sorry.
Yeah, it's okay. So as it's said that mass density is written as mu, which is of the small volume we assume del x, del y, and del z. So let's say that mu is equal to some mass m upon del x by del y del z. Then the volume of the region in expansion. Then we calculate its expanded and scaled volume to a cube del x del y del z element, and we see that the new energy density, not mass density. Actually, mass and energy are equivalent, so we can say energy density directly. So that is why we have this new rho, not mu, because when the space expands, the energy will change drastically. That is why you see its scale factor also changes through the expansion. So basically, the new rho is mass upon volume. The mass would be calculated from mu, which is mu times del x, del y, and del z upon the expanded volume element, which is a cube del x, del y, del z. The del elements get cancelled, and mu upon a cube is the resultant formula for the energy density in the expanded universe element. I hope that clears it out.
That's actually that's a good explanation. So we use the naturalized units, right? C equals to one there.
Yeah.
Uh, Sorry, did you said C is equal to 1?
No, I'm like do so we use the naturalized units here, right? Because energy equals to mass happens in that one.
Yeah. C is equal to G is equal to, and I guess H is also is equal to 1, which is
Yeah, I
constant.
suppose. Hmm. Okay, thank you.
You're welcome.
If no one else has more doubts, then I'll continue with the presentation. Okay.
Yeah, I think you can continue.
Yeah, I'm sharing my screen. So I hope it's visible. Wait, it is visible, I think.
Yeah, it's visible.
Yeah. So 2.73 degrees Kelvin is um, a significant number in astrophysics, if you can see. Does anybody know why it holds importance or what does it represent? You
It's
can
the
say it out loud
temperature.
then.
It's the
The
temperature of the cosmic microwave right now.
Yeah, exactly. So it is the temperature of the cosmic microwave background, the map of which you can see on the screen. And how we figured it out is there are a lot of different ways. So we have Planck's formula here, which relates the intensity and temperature and frequency of light. And if we apply binomial approximations and some mathematical shenanigans, we'll get that lambda equal to hc by kt. Um, And from here, because we know the wavelength of the light that we see, we can calculate the temperature to be roughly 2.73 degrees Kelvin, more or less. And so this is why it's called the temperature of the CMB. But you might ask, I mean, it's not like we can go out and touch it, right? What does it mean for the CMB to have 2.73 degree Kelvin temperature? So what it means is that if you place a perfect black body in space, by the way, the CMB is one of the most perfect black bodies that we have seen. And so if you place a perfect black body in space, it will reach an equilibrium temperature of 2.73 degrees Kelvin if the only method of heat exchange is radiation, because it is being bathed in that temperature of light from everywhere. So not everybody knows how the CMB formed and how we did discover it. So first we'll see how we discovered it, and it was kind of on accident. So here we have Robert Woodrow Wilson, and on the right we have Arno Penzias, and behind them is the Bell Laboratory horn antenna. And they were conducting some experiments related to microwave radiation from space, but what they were noticing was that they had constant background noise every time they tried to calibrate their instrument. So they tried everything. They removed bird droppings from the telescope. They tried to make their instrument more sensitive, and they tried to calibrate it, but it was to no avail. The noise was always there, and it was constant, and it was in every direction. So a colleague of theirs suggested that it might be the cosmic microwave background, and this was already being theorized by some other scientists. So they met up with them, and then they worked on it, and then won a Nobel Prize for this. So the discovery of CMB was not technically intentional. Then, I mean, you might wonder why it is there in the first place. So, well, for that we'll have to talk about decoupling and recombination. And they sound like opposite things, but they refer to the same events. So what happened was when the universe was born, there as you in the first it was very radiation dominated, and it was a hot plasma which contained electrons and protons everywhere. And whenever light tried to pass through, it was always scattered by particles. What happened when the universe was about 380,000 years old was that cooled down to 3000 Kelvin, and so the electrons and protons started to recombine stably to form hydrogen atoms. And what this allowed was that to let the light pass through basically unaffected and undeviated for the majority of space. And so the universe became transparent. Before it was opaque, and now it was transparent. And this is the light that we see in the CMB from the early universe, where light was first allowed to roam freely. This is called recombination because protons and electrons recombine to form hydrogen atoms, and it's called decoupling because photons and matter could now were decoupled. They were not always together. So one interesting thing, if you notice that, I mean, at that time it was 3000 Kelvin. Why is it now 2.73 degrees Kelvin? At that time, the universe was 1100 times smaller than what it is now. So if we apply cosmological expansion to the light, it will expand by a factor of 1100. And if you divide 3000 by 1100, you will get roughly 2.73 degrees Kelvin, which is what temperature we see to what is the temperature that we see today. Um, Moving on. So in astronomy, like in all other sciences, there is always its fair share of boring stuff. Like you have to look at objects, you have to classify them, you have to catalog them, you have to do all this mundane stuff because it's important for the reason that sometimes we find exceptions that lead us to new theories, very new interesting theories. So on my screen is NGC 4414. It's an image taken by the Hubble telescope. There is nothing inherently special about this galaxy. I've just taken it as an example. So what happened was scientists were trying to map galaxy rotation curves. Now, what these are is it's basically the graph of the velocity of a star with respect to the distance of the star from the center of the galaxy. So what we expected to see was, because the galaxy is the brightest in the center, we assumed that most of the mass was in the center, which is a decent assumption. And if we apply the approximate guess that suppose it's like a solar system where most of the mass at the sun and in the center, then the velocity should fall off after the peak and it should be a downward sloping graph. But that is not what we saw. This is what we saw. The red one is the prediction that we had, and green is what we actually see in real life. And this is not special for any one galaxy. We have seen many galaxies follow this path. And you can see a simulation over here of the two graphs and how they will rotate. It's taking a time to load. Yeah. So if you see on the left is our predicted one. On the outer edges, you see that matter is moving very slowly. But here, if you see on the outer edges, it is moving much faster compared to here. And this was very unusual because for this to occur, instead of the mass being concentrated at the center, it would have to be distributed more or less homogeneously throughout its entire extent, which is very unusual because we can't see anything. So people were confused as to why this is happening and how to resolve it. Does anyone know what the answer to this mystery is? You know, you can unmute and
Dark
answer.
matter.
Yeah, that's exactly right. Dark matter is the answer. It's Dark matter is actually not exactly a confirmed thing. It's more of a hypothetical object that we have come up with to explain this, because there has been no experimental concrete evidence of dark matter existing. And we have tried many things. I'll tell you about what we have tried to discover it. So, as I said, it would be more or less homogeneous distribution. Here is an depiction of the Milky Way, of with the blue part being what we assume to be dark matter. Like, this is not actual. This is more of an artist rendition. You can see that it's supposed to be more homogeneous so that the rotation speed matches with what we see. Let's look at the different types of dark matter that we have theorized. We can categorize them in two ways: by velocity, which is cold dark matter, warm dark matter, and hot dark matter, and the increase in speed. So cold dark matter is the slowest, warm dark matter is in between, and hot is the fastest. In this, cold dark matter is the most preferred one because theoretically what it tends to do is form clumps and it will seed the beginning for galaxy formation. Warm dark matter also does that, but only to an extent. And hot dark matter, it's difficult for it to seed galaxies. On the right, we have theoretical candidates based on the ones on the velocity. So weakly interacting massive particle, WIMPs. Scientists have a great sense of humor when it comes to acronyms, by the way. So the WIMPs are based on cold dark matter, and they are theorized to be a particle which have masses more than protons but do not interact with other matter other than gravitationally, or rarely with weak nuclear force. Axions are a candidate which is they are theorized to be trillions of times lighter than electrons even. Primordial black holes is an interesting concept. It is so in theory it's said that when the Big Bang happened, lots of these tiny black holes were created and they're still roaming around the universe. And because we can't really observe black holes that well, we can't detect them. And these black holes are what is causing the more gravitational attraction. And then we have massive astrophysical compact halo objects, MACHOs, another great acronym. And this basically says that objects like dwarf planets and other object but does not emit light is what's causing this. From all three of these, the most promising is WIMPs. Machos is almost disproven completely. So right now, the most research is going on WIMPs and cold dark matter. And so if we move to the next slide, this is the Lux Zeppelin detector for dark matter. It's in South Dakota, and it is currently the leading source for dark matter research. And what it has done in the past years is it has created a bound for what size dark matter can be. So this is underground, and it uses 10 tons of xenon gas to detect it, because what they expect is that the WIMPs will interact with the xenon nucleus and create small bright flashes of small, not bright in terms of the sensitivity of the experiment. It will create flashes of light which the experiment can detect. It is very similar to how we detected neutrinos first. And in fact, this detector does detect a lot of neutrinos, and that is what is holding it back right now, because right now um, it had 400 days of evidence roughly that if WIMPs exist, they won't be in the range of 3 to 9 giga electron volts by c square, because they took all the readings and they calculated the confidence score with which they can say this, and it was about 90%. But as they go smaller and smaller regarding to the mass, they will encounter a neutrino fog, which is basically that neutrinos are coming in from everywhere from the planet, and they will start mixing in with the readings and creating noise, and that should be a big issue. Right now, what they are trying to do is they are trying to detect heavier particles on the very heavy end, around 100 giga electron volts per c square, and this will go on till 1,000 days, roughly till 2028, and they will release their next readings to the world. And if there is dark matter in that range, it will probably detect it. There are other very interesting ways of detecting dark matter that are going on right now. Some of them involve using superconductors. One of them involves surprisingly sugar. There was a paper released in February of 2026 that sugar crystals, because of the structure and because they contain hydrogen, they can be used to detect dark matter. And first of all, they're experimenting if they can use to detect normal matter first. And the paper released in February was um, proof that it is possible, but whether it can detect, whether it is sensitive enough to detect dark matter or not is not yet known. So you might wonder that how do we know that this is a different particle entirely, and how can we be so sure that this is not an issue with our current gravitational theory? So why xenon? That is a good question. I think I'll have to read the paper for figuring out why xenon is there. Yeah, I can link the paper in the chat afterwards, or maybe in the group if you want. So as I was saying, the this is the bullet cluster, and it's believed to be the collision of two big galaxy clusters. And what happens when they collide is that the gas, which is very high speed gas and very high temperature, when it collides, it becomes more high speed and releases X-rays. And the red part is what you see. It was taken. The red part is the X-rays, which were taken by the Chandra telescope, and the blue part is where we theorize all the dark matter to be. Now, how did we come up with this? Well, if you see, we expect most of the mass to be where the red part is, because that is where most of the gas is. That is where most of the X-ray emissions are coming from. And that is where most of the mass is. But if we check via gravitational lensing, because that is more surefire way of, I guess, discovering where the mass is, or where space-time is being bent. So we discover that the center of mass lies roughly around those blue patches that you see, where the gravitational lensing occurs more. So if suppose in our gravitational theory we were just saying that our gravitational theory is wrong and gravity is actually stronger than we thought, then this disproves that, because if it was stronger, the center of mass would still be near the red part. However, it's not the case. So this is one of the biggest evidences that this is not an issue with our gravitational theory, but rather it is something that we are not able to detect yet. This is a little maths regarding the dark matter density. I'll be honest with you, in my section, there isn't a lot of maths regarding all of this. It's more of a conceptual understanding of what actually is. If you can see here that the mass density has been derived here using RS, scale radius, and scale radius is defined as the radius where the brightness of the center of galaxy has fallen off by a factor of E. So you can check the maths in your free time actually, because it's not that much. And we have dark energy as well. In in the 1900s, we saw we thought that the universe expansion should be decelerating, and when they actually saw it, it was actually accelerating. So dark energy was thought to be the source of that. Dark energy is even more hypothetical than dark matter because nobody really knows what it is. As Siddhi said, one of the leading candidates is that it is the an energy present everywhere in space, as in vacuum energy. It is the default energy of space, and basically, you can say it's the mass of the vacuum technically, although it does not make much sense to say it that way, at least intuitively. So we do not know much about it rather than other than the fact that it is accelerating. This is the energy distribution of the entire universe. As we have seen, dark energy 69%, dark matter is 26%, and normal matter is 5%, which is insane to think about since the only part we see of this is the 5%. And together, these three make up the lambda CDM cosmological model, which is the model for the universe after the Big Bang. The lambda stands is a representation for dark energy. CDM is cold dark matter, and matter is also part of the theory. So that is the current model that we have. There are many issues with that model which people are still trying to resolve or wondering whether we should adopt a new model entirely. And that is what is currently going on this field. So I mean, thank you for attending this lecture. If you want, you can ask questions right now. If you want a bit more of the maths on the latter half of the presentation, I can give them as links while I send the link for the presentation as well. Apart from that, does anybody have any questions?
One thing,
Yeah.
so in the energy distribution, again, we are using energy as well as the mass method
Oh,
in the same graph, right?
yeah.
And
It's the
it's
mass
also in
energy
the
basically.
naturalized mass energy.
Yeah.
Mass energy.
Yeah. Basically equal to MC square.
So
Yeah, you're right.
equal to M. Okay, take it.
Yeah.
Thanks.
It looks like nobody
This
else has any other.
this
Yeah.
this one last thing. So we chose xenon, right? Please do share that paper, by the way.
Yeah. I will definitely share that paper.
And we use xenon. Can we not use any other noble gas?
Yeah, that's exactly what I'm saying. I honestly don't know why exactly we use xenon and why we don't use anything other than xenon. So I'll check that, and if I get an answer, I'll forward it in the group as well, and I'll share the paper as well.
Please do. That will be great.
Yeah.
Thank you.
Problem. Any other questions? So I think we'll end the meet then. The assignment will be shared to you by today evening, as well as the recording and the links. And apart from that, have a great day.